The next type of reaction that we're going to learn about is called the single replacement, or again, sometimes also known as a single displacement. I'll typically use single replacement, but you can use either one. The basic definition comes down to where one element replaces a similar element in a compound. Now, when I say similar element, we're basically talking about element type. Generally speaking, it's going to be metals versus nonmetals. Metals will replace metals. Non-metals will try to replace non-metals. Here are some examples, or at least some generic formulas and equations that will help you illustrate that. So the first type here, you can see the A plus BX yields B plus AX, where in this example, A and B, these are your metals, also hydrogen. Even though hydrogen is not a metal, a lot of times it behaves like one, where X then is your non-metal slash your anion. So you can see right here that A and B, right, both these serve as the metals that are present, and these two swap with each other, so now you have B, and then A is now paired with that anion. The other type of a single replacement reaction is down here. In this case, you have X plus AY yields Y plus AX. Once again, in this case, we have nonmetals replacing other nonmetals. Your X's and Y's are some form of nonmetal, and they're replacing each other. Right, so make sure you know that we're not trying to replace different types of elements. Again, all stays within the same general category. The one weird exception, of course, is hydrogen, which we know is a nonmetal, but oftentimes behaves and is treated like a metal. So let's do the first type. This is the one where it's going to be single replacement of metals, and I've rewritten the actual generic equation there. So A plus BX yields B plus AX. This is where metals replace other metals, right? So let's see this first example here where aluminum foil and lead-2 nitrate are going to react together. So we've got aluminum written here, we got lead nitrate. Now, we want to make sure we understand why this is considered a single replacement, right? Because, well, if you notice, you have a metal, Pb, and some non-metal. In this case, it's going to be an anion, generically nitrate, right? Because it has a bunch of non-metals involved. So that's going to be your positive and negative parts of the ionic compound. And then this Al over here, right, aluminum, that's a metal. So what's going to replace the other one is that this aluminum is going to come in here and effectively kick off the Pb. And now we're going to form a new compound where it's aluminum and nitrate. You see that over here where it's aluminum nitrate, Al nitrate. Then the Pb, right, that's the substance that gets kicked off by itself. So that, therefore Pb is by itself over here. So this looks like a single replacement. It looked like one thing was replaced. In this case, the lead was replaced by aluminum. Now, I also want to, before I move on, right, that's kind of generically speaking, in terms of the details, the specifics that you should be looking for, notice how the aluminum, right, is by itself at first. It has a charge of 0, and then when it becomes a compound, it has a charge of +3, right? That's one of the ones you're supposed to memorize. And then lead, right, over here, lead, this is a +2, and we know that because there's 2 nitrates, right, because nitrates are individually -1. So it's important to recognize that, because there's 2 nitrates here with lead, that doesn't mean that we're also going to have 2 nitrates here with aluminum, right? It depends on aluminum's charge, which is different than when Pb was bonded to it. So let's make sure we're clear about writing out legitimate compounds. Let's not just copy what we see on the left side and make that also what we appear on the right side, right? So it's not just going to be NO3 and then become NO3 over here as well. It just depends on the cation that is bonded with. That's going to be your single replacement reaction. The next example here, an iron bar is added to water and produces an iron 3 oxide solid and a gas. So in this case, let's go and take a look at the setup. We have iron, right, by itself, and then we have water right here, right, and that is going to undergo some kind of a reaction, right? It's not just dissolving. In this case, it's telling us that there's going to be a reaction. So what happens here? Well, in this case, iron is the single metal by itself. Over here, it's a little bit weird, but hydrogen in this case is acting as the metal. I'm air quoting that word, metal, because it's not really metal, right? But again, it behaves in that way, so we usually treat it like one in these examples. So it's going to produce an iron 3 oxide solid. So that's right here, iron 3 oxide. And you see that it's got the solid with it, and then some gas. It doesn't state what gas it is supposed to be, but just recognizing that since we're replacing H's, or we're basically taking the iron and kicking off the H, that the resulting hydrogen is going to form a gas. And of course, it's got to be H2 because it's diatomic, not just H. So then you would see that you have H2 gas that's being formed, and of course, it states the matter appropriate, and then you can go through and balance it out afterwards. So these are examples of single replacement reactions. They're fairly straightforward, again, in the overall generic idea, but you do have to pay close attention to exactly what the new formulas are going to be and what state of matter they're supposed to be in based on the language. Let's do a little bit of practice here. We've got a couple of examples here that I think you will be able to apply this idea of single replacement to. And of course, I've recreated this little section here, which is kind of a guide, a nice little guide to remind yourself of what to do for these. So let's start off with this first one. Potassium metal is added to a sample of a solution of silver nitrate to produce soluble potassium nitrate and silver metal. So this is going to be the situation we have. Let's go ahead and walk through the process of changing the names of formulas. So let me go do that for you right now. Okay, so just a quick translation from the names of the formulas, and making sure that you can do this as well. If you need to, you can always go back to double check that this is accurate. Then we go ahead and figure out that this is going to be the type of reaction that we're focusing on, which is going to be single replacement. Do we see that this is single replacement? Well, we have K, right? We have Ag. These are two metals. Ag is bonded to a bunch of nonmetals, the anion here. So this whole compound right here is an ionic compound. And it looks like the K is kicking off the Ag, because over here Ag is by itself, and now K has now bonded with the NO3. So it looks like it's going to be a single replacement. One thing was replaced. And in this case, it's the metal replacing the metal. Let's go ahead and add in the states of matter according to the language. All right, and then let's finish it off by balancing the equation. So in this case, we have everything balanced as is. No need to add any extra coefficients. Now, if you notice, if you've been following along up here on this section, I haven't really been following exactly step by step what to do, and that kind of is a sort of something that you can do with practice. But I basically hit all the marks, right? I went ahead and identified changed the names to a formula. I identified the type of reaction, right? Notice that this single metal is replacing this one that's already bonded to something else. The predicting the product wasn't necessary because it was already done for us, so the language told us that in here. We want to balance the equation. All right, we did that already. And then we also have to identify the state of matter of each substance, which we did also, and not necessarily in that order, but which we did based on the language we're given. Finally, there's this little line about determine if you need to apply the activity series or the solubility rules. And that's something we haven't really addressed here necessarily. The activity series especially we'll get to later on. But that's effectively how this works. Let's try the second one. Copper wire is added to a beaker of iron 2 sulfate solution. Right, so this is one of those problems where you're given not a whole lot. You're just kind of given basically what looks like the reactants, right? You're just given one thing being added to the other, and that is it. So let's at least do what we can. We know that we can translate these. Let's do that now. Done. So what do we do with this? Well, again, even though this section that we're learning about is called single replacement, let's kind of view this out of context, right? Let's see that we at least acknowledge that there's one metal by itself. You have metal nonmetals, or at least an ionic compound over here. And you can see that, well, it looks like it's going to be maybe a situation where this replaces this, right? The Cu replaces the Fe. And that's very much what you expect here, right? Because this is kind of within the context of these kind of problems, and we're not really going to go outside of that. So you can take comfort in knowing that this is going to be a single replacement because the Cu is going to replace the Fe in that same format that we've seen a couple of times now. So let's see how this works. Let's go ahead and swap them out. So the Cu is going to kick off the Fe to make SO4. And then you end up forming a compound, CuSO4, and then iron by itself. Now hopefully a little kind of red flag went off here. For those of you kind of seeing what I was doing, the CuSO4, I don't know that this is the formula. And I have to be honest with you, I probably should have given you more information about this product because the way it's written right now, we know that copper is a +2 ion, right? But unfortunately, copper is one that is multivalent, right? I don't know what copper's charge is always going to be. Compare that to things like, potassium or magnesium or calcium or strontium, any of the group 1 and group 2 elements. We know what their charge is going to be when they become an ion, but for copper, it can be multiple ones. So I have to apologize here. I didn't really look ahead for this one. To know that copper is one that would just be +2. But for the sake of this problem, just to kind of get something down, let's assume that copper is +2. And that way we can say that this compound formula is just going to be CuSO4. If copper was in fact a +1, I would probably indicate that some other way. But for this one, we're assuming it's +2. Whatever the case, we have a product here, CuSO4, and then we have Fe also, right? So the Cu kicked off the Fe. Now, we need to proceed with the rest of this, right? Because we need to, according to this right here, we identified the type of reaction already. We predicted the products in this case. We need to balance the equation, which if you look at it right now, it's actually balanced as is, so no need to add any coefficients. And then identify the states of matter of each substance. Now, this is going to take a little bit more context because you have to be a little bit more aware of the environment. So copper is being added to a beaker of solution. So you kind of imagine that effectively you have a beaker, you have some solution in there, and then an iron bar is being thrown in there. So you just have to kind of contextualize this, and so that helps you identify the states of matter. Copper wire, excuse me, not a bar, I said bar, but you get the idea. It's a wire. That makes sense to be a solid. FeSO4, iron sulfate, that's a solution, so that's going to be aqueous, right? We're assuming that substance has been dissolved in the water that's inside the beaker. And then you have two products, CuSO4, which is going to end up being unknown, right? Nothing stating anything about this. But remember, this reaction is happening in this watery environment. So CuSO4, what state of matter does it get? Well, we have to kind of basically just use our solubility rules to kind of predict what CuSO4 is supposed to be according to the solubility rules, because we're still in a watery environment. So aqueous, right? Turns out that's going to be aqueous. And then iron, well, I hope you know that when iron is in its pure form, it's going to be a solid. So let's go ahead and throw that in there as well. Let's handle number 3 then. Number 3 is going to be the hydrochloric acid slowly dripped onto a strip of zinc. Well, hydrochloric acid, as you can imagine, that is something that's going to be dripped. That's going to be a liquid of some kind, but let's first start off by just translating it. HCl, and it's going to be added to a strip of zinc. Right? And then once again, we're in a situation where we're just given effectively reactants. We're not really told a lot more, but we have some context clues we can use. So in this case, we have zinc, which is a metal by itself. You have HCl, which, you know, isn't really anything that seems to fit what we've done. H isn't really a metal. Cl is a nonmetal, though. However, again, this is one of the situations where you do have a H acting as a metal, right? So it's one of those strange situations. So let's go ahead and have zinc and attempt to replace the H. So what do we get? Well, zinc is going to be over here, and it's going to be combined with Cl. It's kicking off the H to make it combine with Cl. In this case, zinc, when it becomes an ion, we know it's +2, right? Zinc is a transition metal, which we normally view as multivalent. But remember, zinc is one of the ones we know is always +2, so we can do +2. Cl then is always a -1. So in order to write the legitimate compound, make sure we know that ZnCl2. And then, of course, the other product is going to be hydrogen by itself. But of course, we can't just write H. We must make it H2 to represent that it's going to be diatomic. Right. Let's go ahead and balance the equation. To do so, we're going to add a 2 in front right there. And then to finish off by doing the states of matter, you're going to have to use some context clues again. So HCl, it says it's slowly dripped onto it. That means this is going to be it's going to be a liquid. Right? Zinc, Zn, this is going to be a solid, right? It's a metal, strip of zinc, it's going to be a metal. ZnCl2, that's going to end up being a solid. We'll talk about that in just a moment. And then H2, that's going to be gas. So let's talk about this zinc Cl2. ZnCl2, just real quick, just giving you context again, the reason why we know it's solid is because it's an ionic compound. Ionic compounds, especially when they're not dissolved, they're just going to be a solid. All ionic compounds we can assume more or less are solids if they're just by themselves. We're not saying any of this is in a watery environment, right? HCl is assuming that it's a pure liquid. There's no water involved. And then over here, H2, right, hydrogen, well, that's definitely a gas, and that's hopefully something you know from experience, but also just, you know, if you consider hydrogen as one of the lightest metals, it's definitely going to be a gas. Let's go ahead and finish out this next one. This case, we're talking about the single replacement of nonmetals. Typically, these are going to be your halogens. It's going to be a halogen replacing a halogen. So repeating this generic form, X plus AY. Notice how the X and the Y are the ones that are replacing each other, right? So the little X kicks off the Y. And again, halogen replaces a halide. Remember, the halogen is a family of metals. The halide is the IDE ending, so it's the ion form of it. So let's take a look at this one. Chlorine gas is bubbled through a solution of potassium bromide to produce potassium chloride and bromine liquid. All right, so what do you see here? KBr, K metal, Br halogen, non-metal. Cl2, also non-metal, so KCl, right, is formed as a result. Right, the Cl comes in and basically kicks off the Br. And as a result, you get Br, bromine. That's Br2, that's a liquid, so that's going to be your diatomic element. All right. Let's try this first one together. Kind of speed things along and go ahead and start translating it now. Okay, so I went ahead and translated it. I went ahead and threw the subscripts on there as well. And you see that it has got to be balanced. To do so, I'll go ahead and throw a 2 in front here and a 2 in front here. All right, so again, how do we know this is a single replacement? Well, the nonmetal I is going to replace the nonmetal Br. And therefore you end up with NaI, and then Br2, diatomic Brinkelhoff, diatomic iodine. Let's try the second one. So fluorine gas is bubbled through a solution of iron 3 chloride, and then gaseous chlorine is formed. Let's see how this is going to be put together. So we've got fluorine gas. That's diatomic as well. That's going to go that on there. And there's bubble through a solution of iron 3 chloride. So that's going to be FeCl3 that's dissolved. And that's going to form something. Now, please do note, right, this is an example of where you have to do a little bit more critical thinking, right? Just because you see gaseous chlorine is formed, right, so Cl2, diatomic, does not mean that it's the only thing, right? Because if you look at it, you notice that the iron, where did that go? Where'd the F go? So in this case, you have to do a little bit more thinking to say, okay, actually, the iron, right, and the Cl, these two are going to replace each other, where the Cl and the F are going to try to swap out. So F is going to try to kick off the Cl. So that means we're going to have a new compound here where it combines iron and fluorine. But of course, we know that since fluorine is a -1 when it's in a compound, that's going to require 3 of these, and the iron is still +3 as it was over here, FeF3. Now, I will say this one's a little weird in terms of the states of matter. We don't really know much about F as an ion, or at least as a solubility thing. So let's just go ahead and assume it's aqueous for the sake of having this done. Otherwise, I really would give you some other better context. And to finish it off, let's balance it. Let's make this 3. Let's make this 2. Let's make this 3 and 2. So once again, nonmetals on nonmetals. Finally, the activity series here, this is going to be one where you're going to take 2 substances and mix them together, but they can't always work just because you write them out as if they work. So in order to identify it, we use something called the activity series to compare elements. So let's go and take a look at what the activity series looks like. And this is what it more or less is. It's a bunch of metals and a bunch of nonmetals. So I'm going to go and draw a little line right here to divide it. So we compare the metals on this section, and then we compare the nonmetal halogens down here. So basically what we do is you're going to identify the 2 things that are trying to replace each other and see if it works. If a more active metal is trying to replace a less active metal, then it works. If it's the other way around, it won't. So let's go and see this example going back up here. Slide all the way back up here. Let's take a look at number 1. It's got K and Ag. Right? These are the 2 relevant metals that are replacing each other. K is trying to kick off Ag. So I need to check the activity series to see where they are in relation to each other. So I have silver down here. Right? And make that mark right there. And then I had K, potassium, which is up here. Is potassium, which is the solo metal, is that more active than silver? Yes, it is. So that reaction that we've got written out here, this first one, is actually going to be something that occurs. But what about number 2? Right, copper wire and iron. Let's see how that one works. So copper and iron. I'm going to get rid of these 2 marks. Copper is here. Iron is here. So copper is trying to replace iron based on this equation that's written right here. So copper is trying to replace iron. Which one is more active? Well, it turns out iron is more active than copper. So in fact, this is going to be a no reaction because the activity series states so. Okay. Go ahead and try it out for the rest of this page, or at least number 3 on this one, and then do the same for these 2 examples with our nonmetals. All right, that'll do it.